Hello, everyone. So today we're going to be demystifying the PE file or mystifying it a little bit. You can decide for yourself. So just a quick introduction. My name is Dominic. I also go by Acrylic. I'm a second-year computing security student here. I transferred here this year. I'm also a red team content engineer for TryHackMe, and I'm an independent contractor for BC Security. I've spoken at several conferences, including Black Hat USA, Black Hat Europe, DEF CON, and in April, I'll be going down to the Kennedy Space Center to talk at HackSpaceCon. So just a little table of contents. We'll be going over a little bit of the introduction of what the PE file is, what a portable executable is, and kind of why Windows uses those. We'll also kind of look at the structure behind that, what they look like, what the headers are, what the sections are, etc. And then we'll do a little analysis, a little seeing what these tools actually look like in the real world and how we can apply them. So what a portable executable is. So a portable executable is a file format, just like any other kind of file format, like a PNG, a PDF, MP4, etc. They need some kind of structure or some kind of definition for how they're going to present their data. So this is going to be used for all executables, all objects, all DLLs, etc. for the Windows operating system. So, like I said, it's going to be a data structure to encapsulate all the information for the application. PE file, you can also see it kind of referenced as a COF file or a common object file format. And these are mostly the exact same. The PE file format specifically is Windows specific. And for now, we can just kind of think of these two as the exact same thing and that their structures are the same. Towards the end of the presentation, we'll kind of look at the differences and see what the difference between a PE file structure and a COF structure is. So the PE file structure, it's going to be split into two different categories, headers and sections. So headers are going to kind of define all of your information, all of your metadata for your PE file or for your COF structure. And then your sections will kind of store all of your code, all of your data, etc. In memory. So PE file headers, they can either be a group of other headers and then pointers to those headers and contain the offsets, or they can just store the values of the field itself. So there are kind of 5 different headers here for a PE file. There's the DOS header, which is just going to be always constant. It's just going to give you all of your constant information for the PE file. The PE header, the optional header, the data directories, which is just where all of the other data and information of the PE file is kind of stored, and then your sections table, which kind of provides you with pointers and different information of all of your sections. So the DOS header, it will contain the DOS stub and then a signature. So the DOS stub, if you've ever seen, maybe you attempt to execute some kind of exe on a Windows application, and you see this program can only be run in DOS mode or cannot be run in DOS mode. That's all that the DOS stub is. It'll also provide offsets that are constant. And so whenever we're kind of interacting with a PE file or whenever an application or library is interacting with these PE files, it's always going to use these constant values or these constant offsets to kind of align itself with the memory. And so one of these important fields is E_LFA new. And what this is an offset at the byte OX40. And then this will go ahead and give you the first address of the PE header. So the PE header and the optional header, like I said, you'll go ahead and get the first address of that PE header from the DOS header. And then from there, you can go ahead and get offsets to all of your other headers. So these are going to contain mostly metadata, mostly information for the rest of the PE structure. So kind of looking at the PE header, we'll have some things like the signature, the number of sections of the PE file, because depending on different compilers, etc., there may be a different number of sections or different types of sections. There will also be a size of the optional header and also an offset of the optional header. So to access the optional header from the PE header, you'll have to take the offset of the optional header and then add the size of the optional header to go ahead and get the address of your optional header. So you're going from your DOS header to your PE header and then doing math to get your offset header. Your optional header. So your optional header will go ahead and just contain a lot more of the kind of information about the PE structure and the subsequent sections of that PE. So things like the image base, the size of the images, the size of headers, and then the number of relative virtual addresses and sizes of those. And one of the most important things here, which we'll kind of go into a little more in depth later in the presentation, is the address of the entry point. And so this is the entry point that it uses for execution. So this will be a relative virtual address that I will always use to begin the execution of the PE file. So like I said, there are some other headers and tables here. So things like the data directories, this is just going to contain a lot more of the pointers of any miscellaneous data structures that aren't kind of already defined by those DOS headers or the optional header or the PE header. So things like your imports and your exports, say you have Windows APIs, different CRT functions, etc. Those are all going to be contained within other different sections that we'll talk about later. And then you also have a relative virtual address for all of your imports. All of your sections also get an entry in a section table. And so for every section, there is a name for the section, so .txt, .idata, etc. You also have a few different relative virtual addresses for things like your virtual size, your virtual address, or like the pointer to the section itself. And then you also have a few different things like the size of it, its characteristics, is it read-write, is it read-write execute, etc. So your PE sections. Your PE sections kind of contain all the actual execution data for your file. So things like the code itself, what does the assembly look like from the compiler. You also have all of your imports. So this will be kind of controlled by whatever your linker is to link between these executables and these libraries to kind of execute these functions. And then you also have all of your data. So whatever information is kind of used by that code, things like your variables, etc., and your strings. So there are a few common sections, all of which will be dependent on whatever your compiler is. So say you're compiling with Visual Studio, maybe you have the CRT section in there. Some compilers include an RData section, some don't. Depending on if it's a P file or if it's a COF file, there may not be a relocation section. So let's see. And then all of the kind of data within most of your sections are going to be stored in parallel arrays, which is where we kind of get a little deeper into these kind of computer science concepts, which I'm going to try and keep to a minimum, but you kind of can't avoid it for things like this. So firstly, the .txt section, this is just going to be the default section to store all of your code, all of your assembly, etc. You also have your .bss section, which is any of your uninitialized static and global variables. So that means that you've only declared these, you haven't actually initialized them at all, and they're not being used. You also have your .data section, which is going to be all of your static and global variables that are actually initialized after you declare them. Also, like I said, the CRT, or the Common Runtime section, this is going to be used by Microsoft's C and C++ runtime specifically for all of its initialized data. You also have a .resource section, which is going to contain things like your icons, your bitmaps for all of your code. You also have the idata section, which will be your imports specifically. So this is going to contain all of the data for your imports or your functions from libraries. You also have your edata, or your exports for all of your files. You also have all of your relocations and a table for all those base relocations. So if a loader, such as the Windows loader or Windows.h, cannot load a file from its linker, then it will use the relocation tables. And then you also have a debug section. This is another place where it kind of differs with the COF headers and with the PE headers, which we'll look at a little bit later. This section specifically is going to end up stored in the .rdata section. And it's going to contain things like your symbols, etc. All right, so here we kind of see how these different sections kind of play in with this overall structure of these sections. So we see that our code is in the .text section, imports in .idata, and then your various different data sections. So here's where it gets a little more technical. So here we see the .text section. This is just the overall kind of look at the program in memory, we see a few different sections, such as the imports, which kind of translate this get message code function. But then we also see our .txt section, which has a jump and a call. So that call will be used along with the .idata section to then go ahead and resolve that get message code import. So our .idata section, this is going to, like I said, handle all of our imports. So this is going to use an array called the image import descriptors. And this is going to be created for every single DLL that's going to be linked by your P file. So things like stdio, kernel32, ntdll, etc. And for every single one of those, it's going to have a little bit of different information. So things like characteristics of the DLL, the time date stamp, different forwarder chains, a name for whatever the DLL is, and then a first thunk. So here's kind of what the idata section looks like in memory. So we see that for every single ordinal number and for every single different API call, there are two different relative virtual addresses for this image import descriptor. So like I said, every single DLL will get one of these, and then whatever ordinal numbers, whatever functions, etc., that imports, it's going to have one for the name, and it'll also have a parallel array for the import address table. And the import address table is what's going to be a lot more user-friendly. It's just going to provide you with a nice table of all the pointers and of all the actual names of all these functions. We also have the export directory, which is a little different than the idata array. This is going to be a structure instead that's going to store all the information for those exports. So things like the name, base, the number of functions in that export, the number of names, and it's going to have a few relative virtual addresses or a few pointers to different things. So it's going to have pointers to all of its functions, pointers to all of its names, and then pointers to all of its ordinals. And so this is important. So say I'm having a DLL that is loaded. That DLL is going to have some kind of export with it. And that export is going to have all of these different things and all these different pointers that you can use. And that's how it's kind of executed in memory. So whenever, say, I'm executing a DLL or say I'm injecting a DLL, what it's doing is going and finding these different pointers and executing them. So kind of here's what the edata section looks like in memory. Again, we see all these relative virtual addresses, and all of these relative virtual addresses have these parallel arrays. So we see that we have the address for every single function. We also have a name for every function, and then we have an ordinal number for every function. So here we only really have 3 functions that are exported by whatever this file is, but every single one of those functions has 3 different characteristics of it. It's either going to be an address, a name, and then an ordinal number for it. So just different identifiers for those functions. So how kind of a P file will execute. First, it's going to go ahead and kind of parse all of its different headers. So the DOS, the P, and the optional. The E_LFA new is also going to be used to store the different things like the offset for the P header. And that's where it's going to go ahead and parse. Basically what it's doing is going ahead and parsing all of its different offsets, so it knows the locations of everything in memory. It's also going to go ahead and parse its section table. So its section table can go ahead and be accessed from the optional header plus the size of the optional header. So like we said, we have our DOS header, we have our P header, and then we have our offset header. After we get past the address of our offset header, and then the entire size, our optional header, and then the entire size of our optional header, now we're at our sections table, and we're at that address in memory, right? So then we can start parsing that table, and then it'll also check for validity. So there's a few different fields for that, specifically in the option header, I believe, that'll go ahead and check for alignments of the file and of these sections. It'll also go ahead and map all the different images to memory. So things like the image base, the size of headers, and then all of its sections as well, all need to be mapped to memory, and it'll use the relative virtual addresses for that. It's then going to go ahead and deal with all of its imports, building things like its import address table and its import name table. and it'll use that. It'll do that by going through the data directories. Like I said, that's all the miscellaneous data structures. So things like your imports, and parse all those things. And that's all of your iData sections. And then it will go ahead and do execution. So like I said, it'll go ahead and rely on the entry point inside of the optional header. And this is where it goes ahead and takes the entry point RVA, or the entry point relative virtual address specifically, and goes ahead and uses that to begin execution. So like I said, there's a few different differences between a P file and a COF file. So oftentimes, if you look at blog posts or articles, they may say that they're the exact same or that they're identical. This is for the most part true, but there are a few differences. A COF file is not a Windows-specific file, so it's not going to have things like the MS-DOS stub or the P signature. It also won't have any kind of optional header or any of the base relocations. And instead of creating a debug section at the very end of its COF structure, it will go ahead and parse all those symbols and then create a symbol table specifically instead of a section. So now we're kind of going to get into kind of interacting with these P files, really getting hands-on with them and seeing what we can do with them. So these are all going to kind of be summarized by different calculations of these offsets and these fields. Again, like I said, all these start from E_LFA new, which is a constant field, and then we can do all of our calculations off of that. And so really any kind of library or function that you may use to kind of access different information of a file, say you're trying to get a file name. All that's going to do is this exact same thing where it's taking pointers, it's taking math, and it's just going through all these different offset and address operations to get to whatever that value information is. So here we kind of see an example of the DOS header. So again, all these are going to start at OX40 or OX3C of that field, which is a constant value of the DOS header. And then everything after that will all be relative of the address space. So I kind of introduced this topic during my advanced Windows talk. And so this is kind of the concept that we can take a DLL or we can take some kind of executable application and we can go ahead and get the hex dump of that. And then really all this is just the kind of P dump of a file. And so we can use this hex dump as our basis to do math and different byte math on it to go ahead and get different offsets for a file. So here we see this is a reflective DLL loader. So here we see that we're starting at the initial offset of E_LFA new, which is OX3C, and then we're just doing different math operations on it. So here we see that we're trying to get the P header offset, and so all we're doing is adding +2, adding +1, and then having different byte operations on that. And so all we're doing is doing this different byte math and doing this different kind of array operations just on this buffer for this hex dump of a DLL. And ultimately, you can just continue going through that for all of your offsets, getting all the values of your fields, etc. Here we also see an example of something called a COF loader. So this is going to be used more for offensive tools, things like Cobalt Strike or command and control frameworks. This is going to allow you to kind of already execute some kind of code in memory, and then you can go ahead and send new code over the wire that's already compiled. So things like an object file. You can send your object file over the wire, and it can go ahead and it can do different copy operations. And it can go ahead and kind of integrate its sections, so all the P and structure information of your object and all of your P file information and the current memory space of your actually executed code. And it can go ahead and add all the functions to that already executed code. And so that's what this is doing here. So instead of doing the math like we did in the previous section, here we already have pointers thanks to libraries and thanks to different variables that were already created. And all we're really doing here now is making different pointers so we get different information. And so here we just see that we're getting all the information for the COF header or the P header. Here we're going ahead and we're kind of parsing through our section table. So we're taking the field that we already had from our PE header, which is the number of sections in the PE file. And we're going ahead and we're looping through it for every single section. And we're getting the different information from the PE section table. So like things that we already mentioned, like the name, the virtual size, the virtual address, et cetera. And then every single iteration of this, it's going to get a new section. So the name will be .txt. The next iteration would be .idata, rdata, et cetera. And then this is a meme that I put in there for one of my colleagues, Kevin Clark. He made a cough loader for Meterpreter, and I just found this while looking for cough loader memes, so I put it in there. So here we have another example. This is self PE injection. So we just see again that here, instead of kind of looping through the section table, now we're going to go ahead and loop through the relocation table. And what that's going to allow us to do is go ahead and copy all of the information of our current process and its image base, and then copy it to a new process. All right, so here we see just a generic DLL that is going to go ahead and pop a message box. So this is just a very generic DLL, but here we see that what it's going ahead and doing is creating an export for the DLL specifically. And like we said, there will always be a relative virtual address or some kind of entry point for that export. So here, where we see our ordinal for that function, we see a name for that, and then we see its function. And so when we were looking at what the edata section was, this is all of the same information here. And then we also see the name for this export, which is boxit. So all the information that we already saw from all those parallel arrays of the edata, that's all shown right here in our export directory. So you get to actually kind of see all of these things that we were talking about in these arrays. And then here is just another tool and another example of how you can kind of interact and get really hands-on with PE files. So here is a tool called Detect It Easy. And so what this can allow you to do is kind of go ahead and load any kind of executable or DLL, and it goes ahead and gets all that information for you. So things like your entry point, your base address, your size, your time date stamp, et cetera. And so this is just another example of it's doing all the same things that we already discussed on the back end, but it's giving you a very nice interface to go ahead and interact and kind of visualize all this data. All right, any questions? Yeah.
So I guess with a lot of this, is this mostly looking at it from like a reversing perspective, or are you looking at this from more like an offensive capability perspective?
Yeah, so this is really important for reverse engineering, obviously, but most of my research has been offensive. So all of the examples that I kind of gave, they can all be kind of used for parsing different things. But obviously, if you're doing something like reversing, you're going to use something like Detect It Easy, where all those things are already there for you. You can easily visualize it, et cetera. If you're doing something like what I was doing with the buffer and with the hex dump, that's all going to be more for offensive things, because I can go ahead and have everything in memory. There's no need to dump anything to a file or on disk, and everything is just kind of there, and it can do all of its own math operations. And it's not really using any functions, et cetera, that could be potentially detected on, because all it's doing is just those pointers and those that math. So. Yeah. All right. Yeah.
Did you have a question? I was just, whenever something like this comes up, like, how did you get there? Like, was it just, oh, I want to do this, and then looking into it, and then just building on it?
Yeah, sure. So the question was kind of how did I get into this, or kind of how did I build upon this? So a lot of this I already knew about Ps. I knew a little bit about it, obviously with a lot of your kind of injection techniques that rely upon it. I was also fortunate enough to do a training where I was kind of introduced into all the P parsing things. And from there, I think that was more when most of those things like were just coming out. And I think that it's becoming a little more mainstream now. with all of your P parsing. And then a lot of the more kind of technical details like the parallel arrays, a lot of that stuff is a little harder to find. And so a lot of that information I kind of found from a Chinese blog post about 30 minutes ago. So, yeah. Yeah.
Google Translate the page.
Yeah. All right. Thank you.